Okay, good morning. Welcome back. We are going to move on to Chapter 2. And if you just take a brief look at the schedule, today's Wednesday, September 18th. We're going to look at Section 2.1. And then on Friday, Monday, and Wednesday, we're going to spend 3 days working with matrices and seeing how that all relates to what we're doing with systems of equations here. And then we have the following Friday, next Friday, for Dr. Lefebvre's inauguration. And then we're going to work on some project and some review and whatnot. And then Friday, October 4th, we'll take our first test. So again, you guys can always find this schedule where you want it. So on Blackboard, I put a PowerPoint underneath course docs and links, and you can just follow along on the screen if you want. And our topic of discussion here today is what we call systems of linear equations. Now, I know you've done this before. I know that you've done this in high school. We've actually done some of it already when we were working on some of those supply and demand, where the supply was one line and the demand was another line, and we found out where the two lines cross each other. That's solving a system of equations. So we're going to look at this, solving them algebraically and working on a little bit of algebraic fluency and a couple methods. We're also going to look at it graphically. We'll use our GeoGebra and our graph to solve. We're also going to eventually look at how we can use our calculators and punch it into a matrix and just have the calculator kind of do the work for us. So there's lots of different ways we can tackle this and different reasons for doing it different ways, and we'll talk about that. So I'm just going to give you what we call a system of linear equations. Notice that we have two equations, and notice that we have two variables. Okay? So I want you to think about this. What happens if we covered up that second equation and why isn't that working? That should have worked. Hang on a second. What happens if we only looked at the first equation? Like if I just look at this equation right here and I just ignore the second one. Can you guys solve for the variables x and y? Like what is x and what is y to make this a true statement? Yeah, you could move it over and say, yeah, in terms of y, in terms of x, y is this. And in terms of y, x is this. What I'm asking is, can you give me a number? X equals some number. It's actually impossible in the sense that there's a lot of different answers, right? Like, I could say x equals 6 and y equals 1. Do you guys agree that that would work? If I put in a 6 right here, I'd have negative 6 plus 1. Negative 6 plus 1 is negative 5, right? So 6 and 1 works, but so would something else, and so would something else. So would 7 and 2. So would 8 and 3. Like there's a lot of answers, right? So can we specifically solve for x and y? No. And if we look at the second one, could we specifically solve for x and y? The answer is no. But if we take both of them together, there's only going to be one x and y combination that works for both of them, right? And we'll talk a little bit about the differences. So you guys have done this before. Notice that this first one says, solve the system of equations by using substitution. And the next slide I have says by doing the addition method. Let's just review this. I know you guys have seen this before. But substitution is an extremely useful tool in mathematics for all kinds of scenarios, not just for this particular one, but you're going to run into it in all kinds of scenarios, especially in advanced algebra courses or calculus courses or something like that. So the idea is, if we could turn this guy into either an x equals or a y equals, and then substitute it into the other one, we're good to go. And Will kind of already said that earlier. Like, we could solve for x, or we could solve for y. It doesn't really matter. What did you say earlier?
Y equals -5 plus x.
Okay, so Will is telling us that y equals -5 plus x. Do you guys agree with that? All I did was move the x to the other side, right? So if y is equal to this, if y is equal to this, then when I go to my second equation, everywhere I see a y, I'm not going to write y, I'm going to write this. What we're doing is we're taking an equation that has two variables and we're changing it into an equation that has one variable. And if we have an equation that has one variable, then we can solve it, right? So I'm going to rewrite this equation, but every time I see y, I'm not going to write y, I'm going to write this. So 2x minus 5y, but instead of y, I'm going to write my substituted value for y equals 1. And now we have an equation that only has x's in it. This feels like 8th grade a little bit. So now I can solve this. 2x plus 25 if I distribute, minus 5x equals 1. And I gather my like terms, negative 3x would equal negative 24. X must be equal to 8. And now that I know that x is equal to 8, I can take it and put it back in up here. So y must be equal to negative 5 plus 8, which would be 3. So I could plug it back in and see if it works. Does it work in the first equation? Negative 8 plus 3 equals negative 5? Yep. Does it work in the second equation? I'd have 16 minus 15 equals 1. Good to go? Okay. Let's try what we call the addition method. Now, I could go and do that same process of substitution, and I could do it on this particular system. Or sometimes I might want to do what we call the addition method. And a lot of you are going to be familiar with this one as well. Let me draw some pictures for you. If I put this in a red box, and I put this in a red box, do you agree that red box is equal to red box? You guys comfortable with that? Anything in a red box equals anything in a red box because it has an equal sign in between it, right? What happens if I do some blue boxes? If I put this guy in a blue box, since it's equal to 11, and I put 11 in a blue box, do you guys agree that a blue box is equal to a blue box? So if a red box equals a red box and a blue box equals a blue box, what would happen then if I took a red box plus a blue box? If I added a red plus a blue, do you guys agree that that would be the same thing as adding a red plus a blue? Red plus blue is equal to red plus blue? Following me? We've already established that. So then what happens if I go back over to my equations and I take this red and this blue and I add them together? There's a red plus a blue. And I take this red and this blue and add them together. Shouldn't the red plus the blue over here be equal to the red plus the blue over here? So what am I demonstrating here? I can add the two left-hand sides of the equation. I can add the two right-hand sides of the equation. And I have a new equation that is also a true and legitimate equation. You guys cool with that? So let's just do that and see if it gets us anywhere. Let's add this red and this blue. So if I add these, this is why it's called the addition method. So if I add 3x plus 5y plus x minus 2y, if I gather my like terms, notice the x's are already lined up, so I'd have 4x. And notice the y's are already lined up. I got 5y and negative 2y, so that gives me 3y. And negative 11 and positive 11 gives me 0. Do you guys agree that this is a valid and legitimate equation? It's accurate and true. Did I do anything wrong there? Okay. So the question is, did that get us anywhere? Did that help us? No. I started out with this equation that had 2 variables in it. I had another equation that had 2 variables in it, and all I did is I produced another equation that has 2 variables in it. My ultimate goal is to do what so I can solve this guy? Create an equation that only has 1 variable in it, right? So now that we've established this fact that we can add, the left side plus the left side and the right side plus the right side, and we've established that it's not going to get us anywhere, right? What algebraic procedure could I do on this so that when I do add them together, I'm down to 1 variable? Can you guys visualize what would be nice if this would work out? We could substitute. We could also do a procedure on one of our equations so that when we do that adding process, that either the x's or the y's eliminate themselves. And maybe you've heard of that before. That's why this method is also called the elimination method, the addition or the elimination method. Do you have an idea already?
Multiply the bottom one by negative 3.
Very good. Very good. So Landon, right?
Yeah.
Landon's done this before. He already sees that if we multiply the bottom equation by minus 3, so that means both the left and the right-hand side by 3. Do you guys see how I'm going to have a minus 3x out in the front of that guy? And then when I decide to combine them together, that 3x and that minus 3x are going to turn into a 0x, hence eliminating them. And then this is going to work. So you just got to be a little bit clever. You got to make a plan. And you got to ask yourself, what kind of algebraic procedure is going to help me here? And Landon says, if I take this guy times negative 3, of course I'd have to do it to the right-hand side as well. That's legal, right? So my original equation is still this. I'm going to rewrite my top guy. My bottom one is now negative 3x plus 6y, I got to distribute, equals negative 33. That was legal, right? I just produced a new equation. And now notice what happens if I add my left side and I add my right side. Over here I get 0x plus 11y equals negative 22. 0x, it's just not there anymore, right? So I don't have to worry about it. Divide both sides by 11. Y equals negative 2. Am I done? I want to solve for x and y, right? But once I've done this, the heavy lifting is kind of done. Now that I know one of them, I can just plug it back in. So I can use my top equation, I can use this equation, I can use any equation that I want. Because they're all true equations. Everything I wrote down on my paper was true, right? So I'm just going to take it and let's plug it back up into this top guy. So 3x plus 5 times negative 2, now that we know what y is, equals 11. 3x minus 10 equals 11. 3x must be equal to 21, therefore x must be equal to 7. And I could tackle it, right? Now, if I would have done substitution, I'd have gotten the same answer. If I'd have done the elimination process back on the previous slide on the first one, I would have gotten the same answer. Okay? So which one is your better method? It depends. You just got to look at what you have, and you got to ask yourself which way is going to be the quickest and the least painful process. And certain ones are going to lend themselves to certain ones. Let me just have you try this. I don't care how you solve it, but what I'd like you to do is I'd like you to set up 2 equations in 2 variables. 2 equations in 2 variables. So first set up your equations. Then, once you have that, then either use a substitution process or that addition process. I don't care which one you do. And tell me if you can solve for your two variables. Now, for your two variables, you can use x and y. If I was doing this, my two variables would probably be c and a. Because my brain would say C stands for children and A stands for adults. But it doesn't matter. Do whatever you want. In the end, I want to know how many children bought tickets and how many adults bought tickets. Let me know when you have an answer. I'd like to peek at it, see if you got the same thing I did. Anybody got anything? What'd you get?
I didn't really do it right, but...
Did anybody, are you struggling coming up with the two equations? Somebody help us out. Who thinks they have two equations that make sense here? Go ahead, Will.
25C plus 50A equals 70,000.
Okay, so I bet he's saying let C equal children, the number of children. A equal the number of adults. He said 25C. What does that expression give us?
Price per person.
It's $25 times the number of kids. So that's the total revenue brought in by children. Then he used a plus sign, and he said plus 50A. What's the 50A mean? $50 times the number of adults. So 50A would be the total revenue brought in by the adults. So if I take the total revenue brought in by the kids and the total revenue brought in by the adults, and I add those two total revenues together, it should equal 70,000. There's one equation. Notice that one equation has two variables. We don't have enough information yet, right? We can't solve that based on only that. We need a second equation that relates A and C. What is it?
A plus C equals 2,000.
A plus C equals 2,000. Because if I take the total number of adults plus the total number of children, it's supposed to equal 2,000. Now I have two equations. Each of them has two variables. Now I just got to decide, how am I going to solve it? I could do the addition elimination where I line up the A's and the C's and the equal sign, or I could do substitution where I solve for one variable and plug it into the other. Did you get something? Okay, very nice. Anybody else got something? Now, it doesn't matter if you used A and C. You could use X and Y. You could use whatever letters you want. So, Will said 25C plus 50A is equal to 70,000. He also said C plus A equals 2,000. Those were the two that he decided to use. Now, when you solved this, Will, what method did you use? Yeah, I mean, substitution looks easy in this situation. Why? Because if I want to solve for C or A, it's one simple step to get where all I got to do is move one to the other side and I'm good to go, right? Now, I'm not saying you can't use that elimination method. If I wanted to, maybe I would take the bottom equation times negative 25, because then the C's would cancel. Or if I took the bottom equation times negative 50, then the A's would cancel. It doesn't matter if I solve for C first and eliminate A, or if I solve for A first and eliminate C. Eventually I'm going to solve for both of them, right? So final answer. Anybody else got one? What'd you get?
1,200.
1,200 kids and 800 adults? 1,200 kids and 800 adults? Anybody stuck? If I were to go the substitution route like Will did, let's say I want to solve for C. So C would be equal to 2,000 minus A. All I did is I subtracted A from both sides. So I know that C is equal to 2,000 minus A. Now I'm going to rewrite my first guy, 25, but instead of C, I'm going to write 2,000 minus A plus 50A equals 70,000. And now I have an equation that only has A in it. I just got to do a little bit of distribution, a little bit of gathering like terms, blah, blah, blah. When I solve this guy for A, I should have gotten 800 adults. 800 adults attended the circus. Now I got to solve for C, so I got to plug it back in. This equation, to me, is the simplest one. I mean, I could plug it back into the other one, too, if I wanted to. But 2,000 minus 800 is 1,200. 1,200 children attended. Okay, here's a similar one. Go ahead and try this quick. Again, you're going to want to set up two equations. Two equations, two variables. Label them so that you mix them up in the end, right? Like C and A, that was pretty easy. C for children, A for adults. Had you used X and Y, you'd want to label it accurately so when you get to your final answer, you don't screw it up and accidentally switch the two around, right? Let me know if you got something. Yes. Anybody else? Obviously, when you get your answer, you're going to want to plug it back in and check it. So I think you're going to want, this is 3 points.
Okay.
Oh, which one are you on? You on the subway one? Did you already do the basketball one?
Oh, no. It's not
Oh,
on there.
when did you open this PowerPoint?
Earlier today.
Oh, because I changed it. That's why yours is different. If you close it and open it again, you'll see this one. So what you're doing here, first you got to tell me what is X and what is Y.
Okay.
Like don't just write down X and Y without knowing what it is. So like X, what does it represent?
The amount of baskets.
It could be the amount of baskets made, but we already know the total amount of baskets is 37, so we don't need a variable for that. Total baskets made is 37. Be more specific. What don't we know? Out of those 37, how many were twos and how many were threes? So you might want to say let X equal the number of 2-point baskets and let Y equal the number of 3-point baskets, because that's what we don't know, right? We know there's no free throws, and we know that there's 37 total baskets. So again, this is back to standard number 1 and all that problem solving that we were doing earlier, where you got to make sense of the problem, you got to write down what you know, you got to write down what you don't know, and then try to put it into some equation that makes sense. What'd you get? Yeah, good. Anybody else got something? So, if this is the total number of 2-point baskets, right? Mm-hmm. Total number of 3-point baskets, I think, there you go. 2 times those plus 3 times those equals that. Mm-hmm. So when you just do X plus Y, what does that equal?
Okay.
Equals what? There you go. Now you got your 2 equations. Now you should be able to handle it.
37.
So you got, so you're saying X is the number of 2-point shots made?
Yeah.
So now you're taking 37 times X. You're saying every time somebody makes a 2-pointer, they get 37? No. See how your equation's backwards? Yeah. What do you got? So you're saying X equals the number of 2-point baskets, right? And Y is the number of 3-point baskets. Well, what happens if we took all the X's and all the Y's and we added them together? What would that give us? The total number of baskets.
Yeah.
That's one of our equations because it told us, right? It says we made 37 baskets. Some were 2s and some were 3s. We don't know how many were 2s and we don't know how many were 3s, but if we take them and add them together, it equals 37, right? So then you got to set up another equation that uses the other piece of information, which is the 80 points. There you go. There we go. So a lot of you were using X and Y. So we said, let's say, whoops, using my ink pen to write on my computer, that's not good. Let's say X is equal to the number of 2-point baskets. And Y is equal to the number of 3-point baskets. How many total baskets did we make? We made 37. Each X is worth 2 points, because I get 2 points every time an X goes in the hoop, right? And I get 3 points every time a Y goes in the hoop, and if I'm keeping score, it added up to 80 points. There's your two equations. How are you going to solve it? Substitution, elimination. You can get some practice on that. So I can tell some of you are, this is easy stuff. Some of you are like, wow, I don't even know where to begin. That's where these quizzes come in. That's where your textbook comes in. That's where all those videos that I give you come in. All of this is available for you to practice. Okay? I want to try one more before we leave class today. By the way, if I solve this guy, what did we end up with? X ended up being 31 2-pointers, and Y ended up being 6 3-pointers. So we could check it. If I made 31 2-pointers, that would have been 62 points. And if I made 6 3-pointers, that would have been 18 points. So the 2s and the 3s would have added up to 80. And that makes sense, right? Very quickly, let's take this exact same problem. X plus Y equals 37. Let me get out of here really quick. I'm going to graph it. Go ahead and open up your grapher. Make my font size a little bit bigger. Okay, let's say I had X plus Y, so I'm just going to type it in. X plus Y equals 37. That was one of my equations. You guys agree? X plus Y equals 37? Okay. And my other equation said 2 points for every X, so 2X, plus 3 points for every Y, 3Y, equals 80 points. Enter. So I now have my two equations, equation 1 and equation 2, on my grapher. I'm interested in the place where X and Y are the same, right? So when I do this graphically, I'm interested in the intersection of my two lines. So if I go to the intersection of my two lines, I go to an intersect point, I click on line number 1 and line number 2, and it tells me that these two equations intersect at the point 31, 6. Well, remember that's X, Y. So that tells me that X is equal to 31 and Y is equal to 6. And I'm good to go, right? So graphing, substitution, elimination, they all get you to the same place. It's just a matter of, which route you're going to go. What would happen if I gave you something like, let me think here. What happens if your two equations were 2x plus 6y equals 9 and 4x plus 12y equals 18. Think about that for a second. I'm going to clear this out. I'll give you those again. I was just making them up in my head. What happens if I gave you the following? 2x plus 6y equals 9, and 4x plus 12y equals 18. First of all, what method might you do to solve for that guy? Could do substitution, right? Which one looks easier, substitution or doing the adding method? The adding method kind of looks easy. Why, Will? What do you think?
Multiply the top one and all kinds of
Yeah, if you multiply the top times what? Negative 2. Do you see how that'll cancel? The x's will cancel. Your negative 4x and your positive 4x will cancel. I mean, we could do substitution, but in order to do substitution, I'd have to move the 6y to the other side. Then I'd have to divide by 2. So I'd get 9 halves over 3y. Now I've introduced fractions, which is fine. I mean, we can handle fractions. But why do that if we don't have to, right? Let's work smart. Yeah, so what happens when we do that? If I run a negative 2 through this, a negative 2 and a negative 2, notice I get negative 4x minus 12y equals negative 18, and I'll rewrite my other one right below it. What happens here? Cancel, cancel, cancel. I get 0 equals 0. What just happened here?
It's like infinite or something.
Yeah, they're actually the same line, aren't they? So if you were to graph these two guys, let me clear off all this here. Whoa. I'm going to clear off everything that I wrote here. If you were to graph these two guys, 2x plus 6y equals 9, we get that. And then when I graph 4x plus 12y equals 18, watch what happens. Right on top of it. It's the exact same line. So every single combination of x and y is going to work, right? I can choose any x, y I want. There's going to be an infinite number of solutions. What happens if I gave you something like this? How about x plus 3y equals 8 and 2x plus 3y equals 8. No, that's not what I wanted to do. Let me try this one. How about y equals 3x plus 8 and y equals 3x plus 1? What's going to happen when I try to solve these guys? They never cross. So if I did the elimination method, like let's say I run a negative 1, or I could do substitution. I'll do substitution. So if I look at my two equations here, if y equals 3x plus 8 and y also equals 3x plus 1, then 3x plus 8 would be equal to 3x plus 1, because y equals y, right? Well, you can already see a problem with that. How could 3x plus 8 possibly equal 3x plus 1? Is there any x value that's going to make this true? No. I could subtract 3x from both sides, and I'd get 8 equals 1. Huh? Where in our universe does 8 equal 1? It doesn't. So is there any solution? No. So this is where your book will talk about like an infinite number of solutions, or this is what we call an inconsistent system. Sometimes we get exactly one answer, meaning that our two lines are going to cross exactly once. Or the two lines are going to lay on top of each other, meaning we get an infinite number of answers. Or the two lines are going to be parallel and they're never going to cross each other, meaning there is no solution. You guys have seen that before? Yeah? Okay. Let me go to the one that I wanted to practice before we leave today. And it's this one right here. How is this one different? Last one. Now we have 3 variables and 3 equations. Not impossible. We're going to use the same concepts. It's just going to take a little bit more time. Okay? Remember when we had 2 equations and 2 variables, our goal was to get it down to 1 equation and one variable, either by doing the addition, elimination, or the substitution. Well, when I got 3 equations and 3 variables, first I got to try to get it down into 2 and 2. And then when I get it to 2 and 2, then I can get it down into 1 equation and 1 variable. See how this is going to take an extra step here? So, some of you might already know where to go with this. Some of you might already have a plan. There's lots of different ways to do it. Let's kind of work through one together. Let's try to get down to 2 equations and 2 variables first. So, do you see an elimination step that might help us like eliminate one of the variables? Let's just choose one of the variables to try to eliminate here. Anybody want to throw out an idea? Who do you want to get rid of? Y or X or Z? Doesn't matter. Let's get rid of one of the variables from 2 of the equations. So let's just look at the top 2. Let's ignore the third one for now. Just look at the top 2. If I just added them right now, are any of the variables going to get eliminated? Nope. I need a positive and a negative that match up such that when I add them, they're going to cancel each other. So how can I make that happen? Let's say I want to eliminate Z. If I wanted to eliminate Z from the top 2, I could multiply, how about by positive 2? In the second one, I'm going to rewrite my top one. 2x plus y minus 2z equals negative 1. That's my top one, right? What happens if I ran a 2? If I ran a 2 through number 2 there? Do you see how that's going to help me? So if I run a 2 through there, I'm going to get 6x minus 6y. Oh, did you say negative 2? I'm sorry, Will. I wanted to do a negative. Everybody see why we want to do a negative? Negative 6 plus 6y plus 2z equals negative 10. Why did I want to do that? Because I wanted these guys to cancel out when I add them together, and now that's going to happen, right? So now when I add them together, I get negative 4x plus 7y. My z's go away, equals negative 11. Did I do that correct? Okay, I have successfully eliminated z, and I came up with a new equation, which I'm just going to circle in a different color so I can hang on to it. I'm going to hang on to this blue one. I'm going to use him in a little bit. Are we comfortable with that? Now I want to go to my other 2 equations. Let's say equation number 2 and equation number 3. Let's get rid of that, what I wrote there. Now let's take my bottom 2 equations. And again, my goal is going to be to eliminate z. Are we comfortable? So let's eliminate z. I'm going to rewrite my bottom equation. It's x minus 2y plus 3z equals 6. And I'm going to run a what through that second guy? Positive 3. Do you guys see that? Because that'll eliminate my z's. So I'm going to run a positive 3 through him. That would give me 9x minus 9y minus 3z equals 15. Now I'm going to add these guys, and notice what's going to happen to my z's again. They're going to go away. So 10x minus 11y equals 21. And I'm going to circle that guy in blue. 10x minus 11y equals 21. Okay, now I have two equations that are both in blue, and now I'm right back to the 2 by 2 that we've been practicing the whole darn time. So now you could solve the two in blue, and when you solve that, what are you going to do in the long run? Yep. You're going to... I missed an x in there, didn't I? Sorry. This should be 10x right here, right? 10x minus 11y equals 21. Now I could solve that guy for both x and y, and then back substitute. Once I solve for one of them, the heavy lifting is over. Substitute in to solve for the second one, and then substitute both of those in to solve for the z that I had from the get-go. You guys want to try it out? Go ahead and see what you get. I'm going to rewrite these equations here. So we had negative 4x plus 7y equals negative 11. And we had 10x minus 11y equals 21. So you got to ask yourself, do I want to eliminate? Do I want to substitute? This one's a little dicier than the other ones because it doesn't look real simple either way, does it? I mean, I could take the top one times 2.5, but then I got to use a fraction. There's lots of different ways to do this. Remember, you can manipulate both equations if you wanted to. For example, what happens if I decided to do the top guy times 5 and the bottom guy times 2? Can you visualize what's going to happen? I'm not saying you have to do that. I'm saying that's what I'm going to do. So negative 20x 35. Oh, my brain's broken here. 10x minus 11y equals 21. Oh, negative 1. Did you get y equals negative 1? Anybody? Yep, sorry. 10x plus 11 equals 10. So x equals 1. So I got x equals 1 and y equals 1. And now I got to go back to my previous slide. So 1 minus 2 times, what did I say? X equals 1 and y equals negative 1. Plus 3z equals 6. So 1 plus 2 plus, it's hard to write on this thing. 3z equals 6, 3z equals 3, and z equals 1? Okay, a big ugly, right? So in the end, I got 1, negative 1, 1, negative 1, and 1 for my three answers for x, y, and z. Will, did you get that too? Do you guys all agree that it is super easy to screw this up and make a mistake? There's a lot going on here. And you miss one negative sign or whatever, or you write something down wrong, and it blows up the whole thing and you end up getting the wrong answer, right? So as you're working on these, attending to precision is super important. What do my variables stand for? Write them down. Sometimes we just do abstract ones where we don't even know what X, Y, and Z were here, right? I mean, we don't even care what they stand for. It's totally abstract. It's just algebraic fluency is all it is, right? So what I want you to do is work on your 2.1 quiz and get some practice on all of this. When you come back, we're going to kind of work with matrices, and then we're going to start using our calculators and our computer so that we don't have to do all the computation by hand, okay? We'll still do a little bit by hand, but I want to get to the point where we can just use our computer to help us. So, see you guys on Friday, right?